Well, hello, my physics minions. It's Mr. G today to talk to you about something that's really important when it comes to the idea of energy and power, and that's this idea of efficiency. And you've all talked about efficiency before, you may just not have known it. Recently, we've talked about this idea of switching from a regular incandescent light bulb into something more like this. And the question is, well, why do we do such a thing? And on the packages, they'll say, well, it's because these light bulbs are more efficient. It will use less power over years compared to this original light bulb. And the question is, how do they know such a thing? So when we talk about that, first we got to actually define efficiency. And efficiency is just the measure of how much energy is wasted by a machine. The truth is that all machines waste some kind of energy. And we're going to talk about where that's involved in a little bit. Machines are useful, though, because they do allow us to use less force over a longer distance to do the same amount of work. So you have seen many of these in action before. These are the simple machines. Wheel and axle, I mean, you see those on cars, inclined planes, or just ramps. Wedges, well, you can think about putting a wedge in between a crack and then slamming it down with a hammer. What's going to happen? It's going to break. A lever, you can think about that as a seahorse. If you change where the fulcrum is, what's going to happen? Well, that means less weight to lift a heavier mass. A screw, think about a screw going into a piece of wood. All you have to do is twist it and it's going to drive down, which is incredibly difficult action to perform. And the final one, and probably the one that most of you have seen in great action, is this idea of a pulley. You've maybe seen a pulley system that's this advanced system which is meant to, over a longer distance, to actually be able to lift weights that are much, much heavier than you could ever lift. So simple machines are fantastic because they really lower the amount of force that we need to use. So we talked about this idea then that machines are always going to waste some energy. It's not a perfectly efficient machine. And typically speaking, we talk about this waste of energy in terms of heat. And this comes from the idea of the second law of thermodynamics that you haven't learned about yet, but you will sometime, I promise. That states that whenever work is done, some energy is going to be converted into this heat. The most basic case is something we've dealt with in Physics 11 a lot, and that's that idea of friction. However, you can think about something like bending a piece of metal back and forth really quick. What's going to happen eventually is at that bend, it's going to start to heat up because there is some of your work that is converting energy into heat. Now, generally speaking, however, the work that we put into it, as far as a machine is concerned, is always going to be greater than the work output of a machine. Again, currently we don't have any machines that are 100% efficient. Therefore, the output work is always going to be a little smaller than the input work. The input work, however, is just the energy supplied to the machine, where the output work is actually the work done by the machine. So we may input a certain amount of energy. However, the work that transpires because of that energy is always going to be less than the work we put in. So when we talk about the mathematics of the efficiency of a machine, we look at it really in two ideas. The first one is if we're talking about work output versus input. In our case, work out divided by work in times 100% will give you what the efficiency of your machine is. However, we may also want to talk about it in terms of power. The idea that efficiency is also the power output divided by the power input times 100%. Now, for those of us that are paying close attention, you'll notice that if we're dividing by a similar quantity, in this case power or work, the units will all cancel, and we're just multiplying by a number, which means that the actual units for efficiency don't exist. But instead, because of this times 100%, we're really talking about the value of efficiency being in terms of percentage. So let's take a look at what one of these questions looks like. In this case, the lever is used to lift a 50 kilogram object 10 centimeters up. To do this, we must apply a force of 75 newtons to the end of the lever, which displaces 1 meter. Find the efficiency. So in this case, I hope you notice that there's some distances, there's some masses, there's some forces. I'm hoping you're relating this to work and power. We know again that the efficiency of a machine is equal to the work output divided by the work input times 100%. So remember that when we're talking about the work in, we're talking about the work that we have physically put into the machine. And if we take a look, that's actually taking place right over here with this 75 Newton force. You may recall again that work is equal to the force applied times the distance. We know that the force applied is 75 newtons. And we know that the distance traveled is 1 meter, which gives us a work input of 75 joules. Now, if we compare that to how much work is actually output by this machine, we have to look right over here. Because really what happened with the work on the right-hand side of this lever, this little box went up 0.1 meters. So if we think about that, let's talk about it in terms of work out is going to be equal to our change in energy. Now, it was stationary at the bottom, it was stationary at the top, which means we can think about it in terms of mg delta H because it's our change in potential energy. If we put in our numbers here, we have 50 kilograms times 9.8. Our change in height is 0.1 meters, and we're going to get a value of 49 joules for our work output. So we have our work output, we have our work input. Now what do? We're going to go ahead and plug the values in. So our efficiency then is equal to our work output of 49 joules by the machine divided by the work input of 75 joules times 100%. Now, how do you know if you have these numbers in the right spot? Easy. If you end up with an efficiency over 100%, chances are you're not on the right track. But if we do this math, we should end up with a nice percentage of 65%. That means for the amount of work that we put into the machine, 65% of that work is actually output by the machine. So there you have it, folks. My advice to you is when you're doing questions that involve efficiency, always think that you're likely going to have to calculate some kind of input or output power or work, and sometimes they give you the efficiency, in which case, again, go right back to the equation and expect that at some point you're going to have to get one of these work or power values. Okay?